Okay, here we go. Hopefully that'll work. All right, so atomic history. First guy we're going to start out with is Democritus. This is the same dude that you talked about probably in social studies in terms of like democracy. He's the guy that came up with the idea of democracy. Okay. And what these guys used to do is they would just kind of sit around and talk. They would talk about their ideas as far as, what they thought, nature was and everything. And one of the things that they got around to talking about was matter. Okay. And he came up with this atomos theory. This is 5th century BC. So this is a long time. Oh, like well over 2,000 years ago. Okay. So he's like, if we keep dividing something down, so we got this rock here, because they probably had a lot of rocks sitting around, we take this rock here and we keep cutting it and dividing it and dividing it. Is there a point that we will get where we can't divide it anymore? And he said yes. And he called that particle atomos. And that's where we get the term atom from. Okay. We now know that atoms have parts as well, like protons, neutrons, and electrons. But, back then they weren't able to really know that. Okay. Other people rejected that, like Plato and Aristotle. But in the end, Democritus really was right. Okay. So fast forward the tape. We're going to go forward into like the 1800s here. This guy named John Dalton, he's a looker. Pretty handsome guy, right?
He looks like...
Want to go to homecoming with him? Yeah?
No, he's dead.
Exactly. He looks... I don't know. I could be shooting yourself in the foot here right now, but he's like Harry Potter to me. With the glasses, especially.
Yeah, Harry Potter glasses for sure. I can see that. All right. So like I said, this is like the early 1800s. And he had this idea like a billiard ball. So everybody knows what a billiard ball is.
Yeah.
You play pool, or you know what pool is, right? With the pool cues and the balls. Okay. All right. So he created the atom based on what Democritus said. And he came up with a few postulates. So things that he believed in. Elements are composed of tiny particles, and they are going to call those atoms. All atoms of the same element are identical, while atoms of different elements are different from those. Cinnamon rolls. I like your sweatshirt.
Oh.
Okay. Now we're going to talk about this guy in a few minutes where we have the same elements that are identical. Okay. We're going to talk about that because that kind of falls apart to a certain point. We may not even get to that today. I'm not sure. All right. So compounds then are composed of atoms from more than one element. And the ratio of those are always whole numbers. So you can't have part of an atom. Okay? So water is 2 hydrogens, 1 oxygen all the time. You wouldn't have like 1 hydrogen and half of an oxygen. That doesn't work. Okay. He came up with this idea of the law of definite proportions. Different samples of the same compound contain the same proportions. So like I said, water. Any sample of water, whether you're here or on Mars or Antarctica, it doesn't matter wherever you're at. It's always going to be 11.2% hydrogen, 88.8% oxygen by mass. He also said that there is a law of multiple proportions. If 2 elements can form more than one compound, the masses of one element that combine with fixed masses of the other will always be a small whole number. Right? And then last, in a chemical reaction, atoms can't be created or destroyed. So that is your conservation of mass or matter law that we talked about last chapter. All right. Soon, so this is like early 1800s, his theory was accepted. But like I said, we have to refine it for some of the stuff that we've discovered since then. Okay? So his laws state that atoms are indivisible, but we know now that we have protons, neutrons, and electrons. All right. Next guy. He reminds me, this looks like some president or something, doesn't it? Just the way he's kind of postured there. All right. This is J.J. Thomson. And J.J. Thomson, what he did, so we're about 100 years further up. So this is 1897. We're getting close to the 1900s here, which is when your parents were born, in the 1900s. The later 1900s, by the way. We're not that old. Okay. So cathode ray, he had a device that shot out negative particles. We call those negative particles now what?
Electrons.
Electrons, right. Neutrons are neutral. Think about their name. Neutron, neutral. Okay.
Huh.
All right. So he had this device and it shot out these negative particles, and he had two plates here. Okay. One was a positive plate and one was a negative plate. And when he shot these negative particles out, the negative particles were drawn to the side of the plate that was positive. Okay. And essentially what he did in that process was he discovered the electron. So he is the person that is credited with discovering the electron. It has a negative charge, and this coulombs is the unit that they use for electrical charge. He knew that the atom itself, the whole atom, had a neutral charge. So what he did was he came up with what's called a plum pudding model. Okay. And I pulled a picture of plum pudding so that you could kind of see what that is, because most of us are not familiar with that dessert. It's more of a British kind of thing. Like we just don't have that very much over here. You could also think of it like Jell-O with fruit. Have you seen Jell-O with fruit in it, where it's kind of embedded in there, if you want to think of it like that? But in a particle diagram, this is what they would have looked like. You would have had these positives, and then you've got these negatives that are kind of scattered throughout. So that's at the end of the 1800s. Was the prevailing model of the atom. Okay. Now think about that, because between this time period and 45 years later, they've developed a nuclear bomb. That's a crazy amount of science going on in just that 45, 50 year period. I mean, they are detonating nuclear bombs over Japan, 48 years after this was the prevailing model. That's a crazy amount of science going on. All right.
They developed that fast.
Yeah, I know. It's crazy. So this guy, Roentgen, he is the one that came up with X-rays, essentially. Okay, so when you get an X-ray, what that X-ray does is it shines through. So you've got the X-ray on top, and then you've got a photographic plate on the bottom. And any material that is very dense, like bone, it will block those X-rays and prevent them from going to the other side. So that is why X-rays work with this. This is also why they always make sure that you take off all your metal before you go in for an X-ray. So if you have a watch on, or earrings, if they're doing something with your head, stuff like that, necklace, Anything that's metal, they will make you take off before you do an x-ray because the x-rays won't go through that material and they want to see like your body, not a piece of metal. They'll oftentimes also slap a piece of metal that says L or R down on the next to your hand or whatever it is. So they know if it was a right hand or a left hand, or a right arm or a left arm, or your left side versus your right side if they're doing a chest x-ray. But that thing will be made out of metal, and then that'll show up on the x-ray so that when they're looking at it, they know what view it was. Now, that is why they take off this for metal for the x-rays. Now, why do they take them off for the MRIs?
I'm assuming the MRIs have to work differently.
Mm-hmm. What does the M stand for? Magnetic, right. So you've got metal, and this thing's spinning around. It will pull that metal off of you. So they always ask people, like, do you have like a hip replacement? Or do you have, that's metal on it? They will ask you if you've got any of these implants that can be magnetized. Because if you can, then sometimes they have to work around that for MRIs. All right. So at the same time as Thomson was working, this guy discovered the cathode rays. You could end up having some of those that you can change, and they're not just electrons, but they are x-rays. Okay. And when we get into chapter 5, Kleenex? Yep. When you get into chapter 5, we're going to talk about x-rays and how they relate to light waves and stuff like that. All right. Becquerel was also in this same time period, and he found that these photographic plates were stored with samples of uranium that they're exposed to not only just light, but either uranium or x-rays, that they're going to, you'll be able to produce an image as well. And then they're not deflected by a magnet. So if you have light and you bring a magnet up, it's not going to turn because of that magnet. Okay. Marie Curie, many of you have heard of her. She's one of the female scientists from back then. And trust me, it wasn't easy being a female scientist back in her day. Even like in the 1950s and 60s, these women that were lecturers, and if you were any ethnicity other than white, you weren't allowed in like faculty lounges and different places like that. Like they just wouldn't associate with you. So things have changed a lot. But she's the one that came up with the term radioactive. And that's where certain particles will emit radiation. So uranium, there's a lot of stuff that emits radiation. The bricks in the wall. Anybody that lives in a brick house, any of those things, stone, natural stone has a certain level of background radiation associated with it. Our bodies are able to handle a certain amount. That's why you can have so many x-rays in a year. Okay. That's why I'm not, as a mom, worried about my kid flying planes all the time, because I know that our bodies are able to handle that. People who are pilots or flight attendants or fly like all the time, they're exposed to more cosmic rays than most people. But again, your body's able to handle it. So as a mom, I stress about a lot of things, but that's one that I don't. All right. She came up with the idea of these different particles. An alpha particle, this is the abbreviation for an alpha particle. An alpha particle is 2 protons and 2 neutrons. There are no electrons. She is credited with beta particles. So they are going to be repelled by a negative plate, which means that they are just a negative charge, essentially a high-speed electron. That's what it is. And then gamma rays, which they have no deflection, and they're just very, very high energy. It's like x-rays on steroids. Okay. All right. Here we go. We're going to move on to Rutherford. So Rutherford, we're fast forwarding, 13 years? So we had Thomson's model. And now Rutherford is going to expand on that. He used these alpha particles. So remember, we talked about these alpha particles. They're positively charged. They're 2 protons, 2 neutrons. So they're going to be positive charge here. He set up an experiment. It's called the gold foil experiment. And if you go onto YouTube, you can see professors like emulating this with like ping pong balls and throwing them through things and stuff. But he set up a system where he was able to diffuse positive charge, and those alpha particles should be able to pass through. So this is what that looked like. He set this up and he expected that all of the alpha particles should be able to pass through here. But he had a few of them that didn't. They got reflected off of that. And if something's getting reflected off, then that means that it has been repelled. Okay? So there was something going on here that was causing a repulsion of positive charge. So the positive charge was bouncing off. Most of the stuff went through, indicating to him that most of the atom is empty space, which it is. All right? But then he had some of these repel. So, like I said, most of them were deflected, but there was something that wasn't. So he discovered what was called the nucleus, and he also named protons. So that was his contribution to all of this. So when he was done, this is his drawing of the atom. This is what he thought the atom would look like. We had this thing in the center with positive charges. That's called your nucleus. And then we just had these electrons that were scattered out. Okay? So that was 1910. Now we're going to move on to Chadwick. This is 1932. And he came up with neutrons. So now we have the 3 particles that we know exist in the atom. We have the electrons, we have the protons, and now we've got neutrons. Okay? All right. This is the model that we use most of the time in here. It's called the Bohr model. Again, sexy, attractive guy. All right. So this is 1913. And he is saying that these electrons are orbiting around the nucleus. And he likened that to the planets going around the sun in the solar system. Different electrons are different distances from the nucleus. And that helped him explain why it took more energy to pull some of those electrons off than others. Okay, we're going to talk about these different distances as we move on in the week. No, next week. I think it comes out next week. And then that helped to explain why some are have more energy than others. And we're going to talk about that when we get into Unit 6. Okay, so today, you've got a little bit of time. If you need me to pull the report for you for your test, I can. You could start corrections right now for the test if you qualify for them. Remember, you can't have had any missing or late or incomplete assignments from Chapter 3. And I try to note that in Google Classroom. And then you could also get 4-1 done probably before you leave as well.